Okay, so last time we talked about how you can have a normal distribution and much of the data is around the mean, and you can actually calculate on average the percentage that is within one standard deviation or two standard deviations of the mean. We looked at that with IQ graphs. Um, the powerful thing about this is even if we cannot sample an entire population, if we can get an estimate of the shape of the normal distribution, we can infer where most values will fall, even values we have not measured. So that is the power of inferential statistics. And we can then use that to identify the probability that two groups are overlapping or different. And if they are different, are they significantly different? And that has a very unique connotation when it comes to inferential statistics. So the thing to realize is that there's a p-value. P stands for probability, so it's a probability value. It ranges from 0 to 1.0, and it is the probability of any difference between two samples being due to chance alone. So if the probability is closer to 1.0, it means the observed differences are likely due to chance. So there's a high likelihood that they are due to chance, and it's not a real difference. And the closer to 0 that the p-value is, the more likely it is that it is an actual difference. It's not just due to random differences in the data. So you can imagine if you had a couple different normal distributions and you're looking at them and you're like, this group over here, this group of cacti up on the ridge and this one in the basin, maybe is in blue, and you're looking at the overlap and how it behaves, and you're trying to determine, are these significantly different enough in these normal distributions? Versus another situation where there's quite a bit different, where the means are quite a bit separate. There's not as much overlap here in this color. So you might think these would be more likely to be two significantly different populations. So before you run the test to determine the p-value, you need to set what is called alpha. And alpha is the significance level of the study. It's generally set at 0.05. And you choose it before you do any analyses. You can't wait to see what your probability value, your p-value is, and then adjust it. So if you're not sure, probably just set it at 0.05. It is the probability you're willing to live with that your data may just be different by chance. So if you want to be more conservative, you would set it lower. And if you want to be a little more open to finding a difference, then you would make it a little higher. But again, 0.05 is the standard. The null hypothesis is that there is no statistically significant difference between the two groups. And your alternative hypothesis is that one group is larger than the other, and not just a little bit larger, significantly larger. So here's our little branching diagram. So you have your p-value, whatever it ends up being. If it's smaller than alpha, so less than 0.05, then you're going to reject the null hypothesis and you're going to conclude there is indeed a significant difference. If the p-value is larger than alpha, so anything above 0.05 all the way up to 1, you're going to fail to reject the null hypothesis and conclude that there's no significant difference. So what we want to do is go into our data set with the cacti and demonstrate this t-test. So we're going to use the equals t-test formula. We're going to choose a range for group 1 and group 2. We're going to choose the tails, the number of tails. You'll see what I mean in a second. And then we're going to determine if it's a paired t-test, a two-sample equal variance t-test, or a two-sample unequal variance t-test. I'll explain what those all are. So let's go over here to our handy data set with the cacti. So we have the cacti in the basin. We've already created the histograms for this. And you can see that we've calculated the average for the basin flat area. So the average is 4.2 in terms of height in meters of the cacti. And in the sloped cliffside, the height is a little bit shorter. It's 3.8. And you can see the standard deviations are pretty similar. So the question is, is this difference significant or not? Is there actually a probability we can look at from those normal distributions to determine what's going on here? And so the big question is, what size difference is big enough to be considered significant given the variation between the two groups? And that's what the t-test tells us. So we've set alpha at 0.05. There it is. And now we're going to use the equals t test. There it pops up. You can click it. And it's asking for the first array. So I'm going to grab and scroll down. You can see the histogram from earlier. I'm going to hit a comma now. And now it's asking for the next array for the next data. So I'm going to highlight that. Here we go. And it's okay that they're different sizes. And now it wants to know, whoops. And you can kind of hover here. It's saying use the arrow keys to select a range. So I've already done that. And you can also go here. And when you click there, it's saying now it wants to know how many tails there are. So tails, you can either put 1 or 2. 1 is when you thought one of your two categories was going to be larger than the other, and you thought that before you did the test. 2 is when you're not sure which was going to be larger. In this case, you just thought there was a difference between the basin and the ridge. You didn't specify which. So we'll say the answer is tails is 2. And then for type, see if it gives you, there it gives you some examples and data. So it's saying type specifies the type of t-test. So you can click here and it will give a little more, hopefully a little more information. But it's saying tails, if 1 uses a one-tail distribution, if 2 uses a two-tail distribution, and then you specify the type of t-test. So 1 is for a paired t-test, 2 is for a two-sample equal variance test. And so we're going to go with a two-sample unequal variance test. So we're going to put in a 3 there. And I'll explain why in just a second. But the main thing is, let's close this out. And we can adjust these so it's a little easier to read. So 0.33 is larger than alpha. So if we head back here, we remember that the p-value, if it's larger than alpha, we fail to reject, and there's no significant difference, we conclude. So going back to the data here, drawing, there we go. Okay, there we go. So if we go back to the data and we see that 4.2 and 3.8, we might have thought that was a big enough difference, but given the standard deviation, it really isn't. These are very similar, and it's not a significantly different height of cacti in the basin versus the sloped cliffside. So there you have it. That's how you would run the t-test. Now let's just go back here and fiddle with if we were to choose a different type of t-test. So one was where one of the types was type 3, which we chose, which was unequal variance. Number 2 is with considered more equal variance. I just want to show you that if you choose 2, it's pretty much the same. So don't worry so much between type 2 or type 3 on the p-value. Now we'll come back to this later, but if you change the number of tails from 2 to 1, our p-value has changed quite a bit. In fact, it's half as much as it was, and we'll touch base on that later. But for now, we conclude no significant difference, and that is what we would report.